Hello everyone, welcome back. In this lecture, we shall see a problem on heat transfer analysis in a duct flow. The last case we saw for cylindrical duct, here it will be a square duct. We shall see the problem definition. Hot air at atmospheric pressure and 80 degrees Celsius enters a 8 meter long uninsulated square duct of cross section 0.2 by 0.2 meter square that passes through the attic of a house at a rate of 0.15 meter cube per second. This is the volume flow rate. The duct is observed to be nearly isothermal at 60 degrees Celsius. Okay, here we have to determine the exit temperature, that is TE, and the rate of heat loss Q from the duct to the attic space. Here if you see in this image, air is entering at 1 atmosphere 80 degrees Celsius at a volume flow rate of 0.15 meter cube per second, and the duct is at a constant temperature of 60 degrees Celsius. Here we have to find out the exit temperature and also the net heat loss from the air domain to outer space. In the previous problem, a constant heat flux was applied on the cylindrical surface, whereas in this case, a constant temperature is applied on the outer walls. So for this condition, we have to find out the net heat transfer loss as well as exit temperature. We will be following a different approach compared to the previous problem in this case. Let us start. First, we shall find out the properties of air at 80 degrees Celsius and 1 atmosphere. Because here we will not be able to find out the mean bulk temperature because the inlet temperature is known but the exit temperature is not known. So we shall calculate the properties of air at 80 degrees Celsius. The properties are given here: thermal conductivity, density, specific heat, dynamic viscosity and Prandtl number. Prandtl number is nothing but mu Cp by K. Okay. Now first let us calculate the Reynolds number. We know that Reynolds number is given by rho V d by mu. But in this case the cross section is not circular. So for such non-circular ducts we have to use hydraulic diameter, that is DH. Hydraulic diameter represents the characteristic diameter of non-circular ducts. So it is given by 4A by P, where A is the cross section and P is the perimeter. So in this formula, if you substitute the value of area and perimeter for a circular duct, you will get diameter. So it is calculated based on that. So hydraulic diameter is given by 4A by P. We shall substitute the value for this duct. 4 into 0.2 square divided by 4 into 0.2, that is the perimeter. So finally the hydraulic diameter is equal to 0.2 meter. Now we shall substitute this d value into Reynolds number formula. But we also need to know the velocity. We have been given with the volume flow rate. So we shall calculate velocity based on this formula. Velocity is equal to volume flow rate divided by cross section area. Substituting the values, we got velocity is equal to 3.75 meter square. Okay, now we got rho, V, d and mu. So next we shall calculate Reynolds number. Substituting the values, we got Reynolds number as 35,765. So this is way above 10,000. So the flow is turbulent. Next we shall calculate Nusselt number based on the Reynolds number and Prandtl number. Since the flow is turbulent, we shall use the Nusselt number formula for turbulent flow. We shall substitute the value of Reynolds number and Prandtl number in this equation. And here note that n is equal to 0.3 as the fluid is cooled. In the previous case, the n is equal to 0.4 as the heat flux was applied and the fluid is heated. In this case, since the fluid is cooled, we have to use n is equal to 0.3. Okay. Now Nusselt number is equal to 91.4, substituting the values. Next, we shall find out the net heat transfer coefficient from the Nusselt number. H is equal to K by D into Nusselt number. Substituting the values, we get H is equal to 13.5 watt per meter square per degree Celsius. Alright, we have calculated the Nusselt number and also the convective heat transfer coefficient H. Next, we have to find out the exit temperature and also the net rate of heat loss. To calculate these two parameters, let us quickly check the theory part on heat transfer loss in a pipe flow. Consider a pipe flow with inlet temperature of Ti and exit temperature of Te, and the surface is at a constant temperature Ts. If you see in this graph, the surface temperature is constant throughout and the inlet temperature is Ti. It increases gradually to reach the level Te, but Te will always be lesser than Ts. Here the temperature tries to reach Ts asymptotically. Okay. Here the delta Ti represents the temperature difference between the surface temperature and the bulk mean temperature at the inlet, and delta Te represents the difference in temperature at the exit. And in general, delta T represents the difference in temperature at any location x. Next we shall write the rate of energy transfer equation. mCp delta T is equal to H into Ts minus Tm into DAS. That is, mCp delta T represents the rate of energy gain or loss in the fluid domain inside this duct, and H into Ts minus Tm into dAs represents the convective heat transfer gain or loss happening from the cylindrical surface. So both these terms will be equated. We can write dAs, that is the incremental surface area, as perimeter into incremental length dx along the length of the pipe. Next we shall substitute this value into the term. Here we can rewrite this dTm as d into Ts minus Tm. Because Ts is constant, this will become 0, and we can bring down this Ts minus Tm to the left hand side. It has come here. We can take H into dAs as H into P dx, and MCP can be brought to the right hand side. Since there is a negative sign here, we can add a negative sign to the right hand side also. I hope this equation is clear. Next we shall integrate this differential equation. Integrating x from 0 to L and Tm from Ti to Te, we get ln of Ts minus Te divided by Ts minus Ti is equal to minus H into As divided by m dot Cp. As represents the cylindrical surface area. Further, we can rewrite this equation as Ts minus Te divided by Ts minus Ti is equal to exponential of minus Has by m dot Cp. So if you know the inlet temperature, the surface temperature and other parameters like H, A, mass flow, Cp, we can calculate the exit temperature using this formula. Okay, we shall use this formula to find out the exit temperature in our case. Coming back to our problem, let us rewrite the equation. Here we can keep T on the left hand side, which is what we have to find out, and the other terms we can shift to the right hand side. The formula is written here. Here we have got the inlet temperature, the surface temperature, the heat transfer coefficient H, but we have to find out the net surface area As and also the mass flow rate. As is equal to the outer surface area, which is nothing but perimeter into length. Here the perimeter is 4A, that is 4 into 0.2 into length 8 meter, which is equal to 6.4 meter square. Next we can calculate the mass flow rate by multiplying density with the volume flow rate. Here the density is 0.9994 multiplied by volume flow rate, that is 0.15. The mass flow rate is approximately 0.15 kg per second. We shall substitute these values in this equation. Therefore T will be given by this expression. Further solving, we get T is equal to 71.3 degrees Celsius. Okay, if you note down here, the inlet temperature is 80 degrees Celsius, the exit temperature is 71.3 degrees Celsius, and the wall temperature is at 60 degrees Celsius. We have found out one parameter, that is exit temperature Te. Next we have to find out the net rate of heat transfer, that is either heat loss or gain. Okay. For Q to be calculated, we need log mean temperature. We shall quickly see what is meant by log mean temperature and try to solve Q based on this value. Let us consider the same example. We shall rewrite the equation which we have recently derived. Okay. We can say m dot Cp is equal to Has divided by the long term, which is on the left hand side. Okay. We know that the net heat transfer rate is given by m dot Cp into T minus Ti, that is exit temperature minus inlet temperature. So in place of this m dot Cp, we can use this whole term which is given on the right hand side. Substituting this, we get Q is equal to minus Has divided by the long term multiplied by T minus Ti. Okay. So if you see, we can take this negative sign to the numerator, that is for T minus Ti, and in the denominator it will be the same value. Next we can add and subtract Ts on the numerator. So we have added Ts and subtracted Ts here. So we can rewrite this whole numerator term as Has into Ts minus Te minus Ts minus Ti. Okay. If you see here, Ts minus Te is the delta T at the exit and Ts minus Ti is the delta T at the inlet. So that's what we have written here. The delta T at the exit and delta T at the inlet. So in place of writing Ts minus Te, we shall use delta T. Therefore Q will be equal to Has into delta Te minus delta Ti divided by ln of delta Te by delta Ti. So here this whole term after Has is called log mean temperature. Therefore Q can be written as Has into log mean temperature delta T ln, and the log mean temperature is given as delta T ln is equal to delta Te minus delta Ti divided by ln of delta Te divided by delta Ta. This may seem a bit confusing, but if you go through this once, it will be easy. So directly you can find out the net heat transfer rate if you find out the log mean temperature. And to find out log mean temperature, you just need to know the delta T at the inlet and the exit. You can simply subtract the delta TE at both ends and divide by the logarithm of the ratios. This log mean temperature is quite important in heat exchanger problems. So we have to remember this formula or calculation steps. Okay. Next we shall use this method to find out the net heat transfer rate in our problem. So if you see here, we have got all three data, that is Ti, Te and Ts. Now we can find out the log mean temperature. The log mean temperature formula is given here. We shall substitute the values. We know that delta Te is minus 11.3 degrees Celsius and delta Ti is minus 20 degrees Celsius. If you substitute the values here, the log mean temperature comes around minus 15.2 degrees Celsius. We shall substitute this value in the net heat transfer rate. Q is equal to H into As into delta T ln. We know H is equal to 13.5 watt per meter square per Celsius and As, that is the outer surface area, is 6.4 meter square. Therefore, Q will be equal to 13.5 into 6.4 into minus 15.2. Here if you see, the value of Q is minus 1313 watt. It means the heat is lost from the fluid domain to outer space. Okay. Finally, we have calculated the parameters, that is exit temperature as well as net heat transfer rate loss. Next, we shall repeat the same problem in Ansys CFX and compare the results with theoretical calculation. Thanks for watching this video. I will see you in the next lecture.